Hi, we're going to talk about implied and maximal domains today. So you sometimes get asked, you get given a function, you just get asked, hey, what's the implied domain here? What's the maximal domain here? So we're gonna go through how to find that today, but also talk about what's the point of this thing. Okay, so I've just told you about a couple of videos ago now that whenever we write a function, we have to write it in this really formal way, and we have to define what the domain is, define what the codomain is, although we always use the real numbers, and say what the rule is. But you'll have noticed by now that in your textbooks, you quite often don't actually get given the domain. You're just given the rule, and the textbook kind of just trusts you to work it out from there. You know, what do you reckon the domain would be for this? Or not even think about it. And so you kind of just have to work it out for yourself. What's the implied domain here? So it's not explicitly given, but we just kind of, it's a bit tedious for us to write down this formal notation every single time. So we just kind of give you the function and let you work out the domain for yourself. So that's what we mean when we talk about an implied domain or a maximal domain. It's just, what are all the possible x's that we could throw in here? So let's just put up a quick formal definition. So an implied domain or a maximal domain is the set of all the arguments or all the x values that work when plugged into the rule for the function. So the rule sometimes excludes certain x values, and so it's just only those x values that are going to work in this case. Right. So where working means the result isn't going to be undefined, so we're not dividing by 0 or something like that. The result is going to be a real number, because we've said that our codomain, our target set, is the real numbers. So it better be the case that when we plug a number into our function, we get something that's in the real numbers. It's hard to think of examples where that's not true with the real numbers, but I promise you that can be a problem. The other sort of trickier situation, the one that maybe takes a little bit more sort of art on your part, is working out when an argument does or doesn't make sense in the context of the problem, or working out when the result that you get doesn't make sense in the context of the problem. So I'll talk about what that means with a couple of examples. Alright, so here are the examples we're going to go through. The first two are what we normally talk about when we talk about a maximal domain. So where we're just given a function and we just ask which x values work. So in this case we've got one that's got a sort of a 5 divided by an x down here, and then the other one's got a square root in it, and I'll show you what we do with each of these. And then the other two are where we'd normally talk about an implied domain, which is implied means you sort of got to work it out for yourself. And so those examples are going to be, I'm going to look at the volume of a box versus cutting out a little corner. We've all done a lot of these problems already. And then we're going to look at the profits of CityLink versus how many cars are driving on it per day. So these two cases are going to be cases that have an implied domain. Now, I've split these up into two: maximal domain, implied domain. These two things technically actually just mean the same thing. They're just all the x's that work. But just as a matter of sort of day-to-day language, we tend to use implied when we're talking about a sort of an applied problem, and maximal when we're talking about a more pure like graph problem. Okay, so let's have a look at those examples. Let's start with this one here. This is called a rectangular hyperbola, this type of shape, and you'll learn about these in a couple of weeks. But let's have a look at what that graph looks like. Okay, so over here we can see that this graph 5 over x minus 4 minus 2 looks like this, and I'll try and talk you through exactly why it kind of looks like this, or at least in particular these bits where it flies up and down really quickly. So what's going on here is that if we take a number like x equals 0, then we're going to get 5 over negative 4, so that's negative 1.25, and we're going to be minusing off 2, so we get a perfectly good point here, something like negative 3.25. I suppose we should use a coordinate point. If we want to find the x-intercept over here, I won't bore you with the details, but that's going to be 13 over 2, and we can find lots of points like that. But one thing we can't do is we can't plug in x equals 4. Because if we plug in x equals 4, we're going to get 5 divided by 0 minus 2. So 5 divided by 0, that's a problem. We don't know what that is, so we don't know what to minus 2 for. And we represent that graphically by drawing a sort of a what we call an asymptote, and you'll learn about that in more detail later, at x equals 4, and what that means is we're never going to actually be able to plug in x equals 4. We can plug in a number really close to x equals 4, so we could plug in something like x equals 3.999, and then we'd be dividing by 3.999 minus 4, so that'd be a really small number. 5 divided by a really small number would be a really big number, and that's why we get this crazy sort of behavior close to that x equals 4, where the function sort of shoots up towards infinity. Now, we technically don't say that it equals infinity, but we can see that it's sort of going that way. It's also true that this thing here will never be 0, because it's always 5 divided by something. So it's also true that there'll never be a y value of -2. But once again, that's something we'll talk about in a little more detail when we look at this type of function in particular. But for our purposes, the key point here is that you cannot divide by 0, which means you cannot set x equal to 4 here. So while every other x value is fine, you can plug in any old x value, any old x value, any old x value, but it just stuffs up at this point here. So the maximal domain for this function is going to be all the real numbers, but not 4. Okay? Alright, so let's look at our square root function here. Let me quickly just draw what that one looks like. If we plug in x equals 0, then we're going to have 9 minus 0, 3. So square root of 9 is 3, so we're going to have that one there. If we plug in x equals 9, then we're going to have square root of 0, that's 0. So that's going to be the x-intercept there. And then it turns out the shape of this thing is kind of a sideways parabola. So it's going to look a bit like this here. Now this point here is included because it is, we can take the square root of 0. But notice we can't plug in any x values any bigger than 9. If I plug in x equals 10 here, I get 9 minus 10. I'm trying to take the square root of -1. It's not going to work. And in fact, if I go anywhere past 9, none of those values are going to work. So the maximal domain for this function is going to be that I can go anywhere up to 9, but I can't go any bigger. So there's a few different ways to write that. I could say it's everything from -infinity up to 9, and 9 is included. Or if I'm sort of taking my cue from what we did previously, I could say it's all the real numbers except for the ones that don't work. And what are the ones that don't work? Well, it's anything strictly bigger than 9. Okay, so that's how we would work with a square root function. So what we're doing here is we're sort of saying, we're going to start by saying all the real numbers, and then we're going to exclude anything that just stuffs up our function. So this is how we find the maximal domain for when we're just given a sort of a rule for a function, and it's just abstract. It doesn't refer to any physical actual situation. Okay. Now we're going to look at what happens when we're looking at an actual physical situation. So I've tried to keep the problems nice and familiar. So we've all done this problem before. This is we start with a plain bit of paper, and we're going to cut out little squares of width x from all the corners, and we're going to construct a box, and we're going to look at the volume of that box. So we can represent this with a little diagram. We start with our flat bit of paper that's 1 meter by 60 centimeters. We're going to cut out this little distance x, and with a little bit of thought, we can see that the rule for this relationship is going to be x, which will be the height of the box, 1 minus 2x, which will be this edge here left over, and 0.6 minus 2x here. And if we were to sketch that function, if we just sort of took this rule as given, then what we're going to get is something that looks a little bit like this. It's a cubic function. It might look potentially something like that. And these x-intercepts here, are going to be at 0 and 0.3 and 0.5. You can verify that for yourself if you like. But we need to start thinking, hold on, we can start excluding some things from our implied domain. Because for a start, we're told that what does X actually represent? X represents cutting into the paper by a certain distance. So it doesn't make any sense for us to cut into the paper a negative amount of distance. So none of this really works. We can have a philosophical argument about whether you can cut in zero distance, and so we might want to make this an open circle, but we certainly can't do a negative distance. So we definitely don't want to include that. I would probably say if you cut zero distance, then you haven't cut. So you haven't really engaged with the problem if you're at zero. So I'm going to make that one there an open circle, and that's going to be where we start. So that's a restriction on the physicality of X itself. What does X really represent? But we also have a problem with some of the values for V, if we think about it. So this is supposed to be a volume. A volume is a physical thing. It's supposed to be taking up space in the world. So it should be a positive value as well. But yet, down here we're getting negative values. And so I'm going to exclude those ones as well. Okay, so they're out. And we can think about why that is. Well, if we start making X bigger and bigger and bigger, if X gets any bigger than 0.3 meters, half of this distance here, then suddenly these cuts start overlapping. And so we don't get a box that really makes any sense. So actually, once we think about that, we can say, oh, wait a minute, okay, this bit here doesn't really work either, because that would require me to have these overlapping axes. So we start excluding. We're not excluding because X values don't work in this function. You can plug in X values perfectly well, and you can get perfectly good answers, and you can even get positive answers over here. But we're excluding those X's because they don't make any sense for the given situation. So let's put an open circle at the end of there, and then if we were sketching this on the implied domain, that only that little graph there in between would be valid. So if we're going to write down what the domain is here, it would be everything from 0 to 0.3. Now I'm not too bothered if you want to use square brackets here and say that a cut of 0 is a cut. Is a box with 0 volume really a box? That's up to you, I think. Last question. So this is the one about CityLink. So let's say CityLink makes a certain amount of profit per day, and let's say that they have to pay $10,000 to all their staff and in road maintenance and all these sorts of things per day, and they make $8 for every car that travels on the road. And so we can write down, okay, well their profit is going to be negative 10,000 plus 8x, and so we got on this axis here we got profit. On this axis here we've got X for number of cars, and then we could just naively sketch this graph here. So let's do that. That's going to have an a y-intercept of negative 10,000, and it's going to be a nice straight line. Oh yeah, straight enough. And this x-intercept here is going to be 1,250 cars. Hopefully I haven't stuffed that up. And there you go. So if all we cared about, if somebody told you in year 9 sketch this graph, then we'd have done it. But there's a couple of things wrong here. First off, just like with the volume, we can't have a negative number of cars. So straight off the bat, this bit here doesn't really work. Can we have 0 cars? Sure we can. We could be going into lockdown any day now, and it might very well be that we don't have any cars going on there, or at least not any cars that are paying the tolls. And then it seems like we could have any positive number of cars from there forwards. But if we think about it, we can't really, because we can't have 1.37 cars. We can actually only really have whole numbers of cars. So our graph really should look like a series of little discrete dots running up the page, representing only whole numbers of cars, not sort of decimal cars. So that means what's our domain here? Well, it's we can write it in a number of different ways, but we're looking for whole numbers that are not negative. So one way we could do that is we could write that it's the natural numbers, but the natural numbers doesn't include 0. So we could write natural numbers union 0. So this is either a natural number or 0. Another way we could write this is we could be a little bit clever, and we could say it's all of the numbers from 0 to infinity, but that's all real numbers, intersect, so another rule to apply now, that it must also be an integer, must also be a whole number. You can probably think of a different way to write that, but those are two that come to mind for me. So that's going to be the domain for this function. And once again, it's not a problem with that we can't plug 1.37 into this function and get a perfectly good answer. It's just that it wouldn't represent anything about the physical situation. Okay, just to quickly summarize, how do you find the maximal domain? Well, you just start by saying, okay, I'm going to assume that all the real numbers work. And then you start excluding things. You say, first off, anything which causes me to divide by 0 is out. Now that's usually only one value in your problem, typically. So that's going to be the real numbers excluding that value. Also anything that causes you to take a square root of a negative number, that's definitely going to be out. You cannot take a square root of a negative number, at least not in methods. And as you learn more functions, so we've talked about square roots and we've talked about 1 over functions, but as you learn more functions, each new function you learn will have certain values that work and certain values that don't. So for instance, we'll learn about logs later in the year. Logs, you need to put in a positive number, so a bit like a square root, but even 0 doesn't work for a log. And then the other thing you need to be looking out for is anything which is unphysical. So that means anything that maybe it makes sense mathematically, but it doesn't make any sense for the actual context of the problem. Okay. One last point at the end there is that all polynomials, unless we're talking about a physical situation, all polynomials have an implied domain of all the real numbers, which is just to say that polynomials are well behaved. You can plug in any old number into polynomial and it'll work. Okay, so every function we've worked with so far this year actually has an implied domain of R. That's going to change over the next couple of weeks. Okay.